Hello everyone, welcome in today's webinar session. I hope you can see and hear me well. If you are having any issue with the audio and video, please mention it in the chat box.
Good evening, fellow alumni and dear students. It's an honor today to be amongst you and participate in this novel outreach initiative, which has been organized by the Geophysical Society of Indian School of Mines. Now, amidst the challenges faced by COVID-19 driven lockdown and travel restrictions, this idea to organize a set of e-learning webinars came up during a conversation I had with one of the co-hosts for this program, Prithvijit, exactly 2 weeks ago on the 13th of July. The rest just fell into place thanks to the renowned ISM spirit. On the brochure, the biographies hopefully highlights a diverse mix of research and implementation in the workplace background that all our speaker alumni come from. I hope the webinar goes on to provide a window of opportunity for students on one hand to get an idea of workflows and areas of innovation that currently drives the oil and gas business globally. And on the other hand, for the speakers, the likes of us, I hope it provides us an opportunity to reconnect with the alma mater. And through the interactive discussions during the Q&A sessions, we get some valuable insights from the current students. So time is of the essence. So without further ado, let me crack on. The idea of including a let us set the scene presentation came up when we were framing the session. We thought, before diving into the details of different areas of the oil and gas business where geoscience has a big role to play, let us spend a short time contextualizing the exploration and production cycle and which areas of activities do the topic that we will touch upon fit in the larger scheme of things. So for this particular session, my session is of two halves, so I'm talking about the first part. I will start with a very brief account of myself before moving on to the objectives of the session. From pores to the wellbore. Exploration and production can be viewed as a set of stage-gated linear processes that needs to be executed within a time frame, or a set of steps that have a close-the-loop cyclicity about it. I will then touch very briefly on the role of geoscience as an enabler for each of these stages of the cycle. This would then be the cue for me to elaborate on the structure of this webinar series. Where do the presentations that you will hear during the course of this week sit in the E&P cycle? Last but not the least, I will expand on expectations explicitly. I feel in any knowledge sharing session, if this is not addressed head on at the onset to manage expectations on one hand and to get the most out of these interactions, we do ourselves a disservice. I will be happy to take questions, but because it's a two-part presentation, the questions may have to wait till the end of my second part, which is on acquisition. But just as Ishika said, if you have a burning question, please put it out there in the chat box. Okay, moving on. Just a bit about myself to provide context. 20-odd years, 3 countries, multiple roles in service companies, both big and small, and operators ranging from startups to mid-size independents to super majors. So what's the point of it? At a business level, every organization has a certain philosophy, culture, and a set of challenges to overcome and execute projects. Working various geological landscapes, it has also given me an appreciation for the complexities of Mother Earth. What aspects of our skills and experience are transferable from one project to the other? And where do we have to hit that reset button and go back to the drawing board? All in all, a great experience, a great ride so far. Don't go by the photos. They are from a long, long time ago when I used to go out to the field. I look nothing like that. Decline. A feasibility study is undertaken, and under conducive circumstances, Why I say so? Because not all fields are conducive to enhanced oil recovery. If only things work, then EOR schemes are put in place to arrest the natural decline of the reservoir, the black curve, with a more gradual slope and keeping the field going until it eventually reaches its economic limit onto abandonment. Okay. Now, changing tacks a little bit. Let us get to the basics. We've done the project management bit. Now let's get into our core work. How do we unravel the mysteries of the subsurface? To your left, this is the Downpatrick Sea Stack in County Mayo in Ireland. Why did I include this for this presentation? The simple reason being this is one of those rare opportunities where you get to see 350 million years of rock layer from lower Carboniferous to recent Holocene, all beautifully stratified and standing 150 feet above the Atlantic Ocean. Now, if only we could see the complexities of the subsurface the way we see this beautiful outcrop without having to, do all the things that we do. The downside of that is most of us would be without a job then. Since this is not the case, let us focus on the next best thing. In two-dimensional cross-sections to your right, you get to see different structural styles. Visualize and map pathways from source to reservoir, migration, entrapment conditions within the reservoir. In other words, you basically, through these sections, start building a story that is technically plausible under scrutiny. So, let me reiterate in generalist terms. The role of geoscience is somewhat scale specific when you think in terms of project. What do I mean by that? Basically, the scale of work depends upon where your project is in the E&P project life cycle we discussed. At a greenfield exploration stage, you look at a basin and play fairway mapping, while for an appraisal and development drilling, you hone in at a prospect level. Once a field is at primary production with single or multiple wells, then the scale of things becomes further detailed, finer. You are looking essentially for compartments within the reservoir and what we call bypassed sweet spots. A lot of other things change, but if you want to keep it simple, just think in terms of scale. Otherwise, the geoscientist, the geophysicist, has the same tools of the trade where he is operating. Okay, I will not delve a lot into this particular slide, but I still kept it to almost give you a story before this. How does an opportunity get to a point where we start actually working on it? There's a bunch of people who get involved, and at that point, the company reviews the opportunity and makes a decision. Should we invest or should we exit? If it's an invest, then we get into all those cycles and linear tenures that I talked about in the earlier slides. If not, we go. The reason I kept this slide is because even at this very early stage, you need a subsurface team. You need geoscientists to do rapid screening. Okay, let me move on. We're coming to the interesting bit. So, continuing with our story building session, we now have a discovery. In the fictitious country of Wakanda, we have a license block offshore, which has struck oil with a discovery. And the Isemite leading the course of the week, you will hopefully find a balance between diversity, going from one topic to the other. As presenters, we will all endeavor to stay true to the objective of bringing elements of practical workflow and processes that are associated with a day job. You need to do listeners or attendees. I could request the students to do some groundwork and come prepared. The topic overview can be a good starting point. Draw up a set of pertinent questions and do not hesitate to ask during the Q&A if you reckon they are relevant and possibly not addressed during the presentation. Keep the Q&A informal spontaneous, but keep it interactive. Last but not the least, a short set of questions will be sent to you for asking about feedback after each session, or maybe in this case it will be at the end. The organizers can confirm. I promise it won't take more than 5 minutes to fill in. Please do it diligently, and it'll give us opportunities to learn and improve. That's all I had when it comes to setting the scene. Now, just because we started a little late, I am not going to do Q&A at this point. I want to move on to the next presentation. Ashika, can you please confirm if that's okay?
Yes, sir. Sure.
Okay, how are we doing for time? We are 30 minutes past.
Yes, sir. 30 minutes.
Okay, so we still have a good 30 minutes, which means 15 minutes for the next talk, which I should be able.
Okay, sir.
Okay, let's get going. So yeah, we have now started on our journey. And the first step is to get ourselves familiarized with seismic acquisition. What I will do here is a very brief overview. It is by no means a detailed, in-depth understanding of seismic data acquisition, because I am not a specialist in that area. But I will try to do it justice, and happy to take any questions, which if I can answer, I'll certainly do so. What am I going to cover? I'm just going to touch upon wave theory basics without going into any details. I will then go into planning and designing surveys, both land and marine in this respect, have some schematics shown. I will then go into 4D data acquisition and just one slide on new technologies, things that are challenging. So everyone in the audience, I'm sure, I mean, if you have non-geophysicists, I beg your pardon, but otherwise, I think you know what seismic waves are. Energy that travels through the earth, for example, as a result of an earthquake, an explosion like a dynamite. Seismic wave fields are measured by a seismograph, geophone, or a hydrophone in water, or accelerometer. Now, the propagation velocity of the waves depend on two things: the density and the elasticity of the medium. We also know that velocities tend to increase with depth, and they range somewhere between, I mean, depending on which units you follow, about 2 to 8 kilometers per second in the Earth's crust. In the mantle, it can go up to 13 kilometers per hour. Now, when you think about velocities, there are two basic types of seismic waves. These waves are called body waves and surface waves. And then body waves we can further classify as compressional and shear. So most of our recording is to do with compressional, and in some cases we also record the shear wave, or we actually extract the shear wave. We record the composite waves. Surface wave, for at least reflection seismic, is a noise that we want to remove. For the sake of time, I will skip going through, starting from the concept of wave equation, Snell's law, partitioning of energy at impedance interfaces, refraction methods, and this whole concept of impedance and reflectivity. I'll assume that you are up to speed with that. Instead, I will spend most of my time on the slide, because this is the one where I've tried to group together the key elements of when you sit at the drawing board and prepare your plan of how you are going to acquire seismic data. So please bear with me. What you see here is basically a land survey with a fleet of vibrators close to a Sabka in the Middle East. And this is a usual marine 3D survey. 3D because you can clearly see there are multiple streamers being towed behind it. Now, seismic field acquisition involves three basic elements: a source of acoustic energy, seismic receivers or geophones, And thirdly, a seismograph or a recorder to collect and store data. Now, when it comes to planning these surveys, let's walk through these series of steps that I have here. 9 out of 10 times, even in a greenfield area, you have legacy data. And one of the first things that you need to do, you have to do is assess bandwidth. I wish I had a board where I could draw what is 6 dB down on an amplitude spectra, which you then intersect to find out what is the bandwidth of your current data at your zone of interest within your reservoir. And of course, one of the key objective is to improve that. So the next step is determining what is it that we are going to do different in the interpretation workflow. Is it going to be the same thing which we did on the legacy data 5 years ago? If not, what is it going to be? And that, in a way, dictates what the acquisition we should go for. The reason I say this is because at one point I will briefly touch upon broadband data acquisition. And broadband interpretation, which we have been doing over the last 5 to 6 years, has been a big step change in 3D interpretation. And acquiring data with the right set of parameters is very important for that. The third step is assess achievable bandwidth. A common reason for failure of seismic surveys is the design of the source bandwidth. For example, what depth should the streamer be towed at? What should be the vibrosize sweep bandwidth? Without taking into account these, we will never get the bandwidth that we do our theoretical assessments with. The next step is about identifying if surface waves, remember I told them they are noise in my case here, so if surface wave scattering is a problem or not. Depth of the source plays a big role in ascertaining what type of surface waves are encountered in the raw data. In marine data, it could be a very hard, what we call rugose seabed. In land data, it is usually the weathered layer or the base of the weathered layer from which we get a lot of peg legs and refraction. Usually at survey designing stage, we use elastic finite difference modeling to identify the dominant wave modes and then plan our receiver arrays and our source depths accordingly to nullify that. So when I talk about nullifying, the biggest, one of the key things that an acquisition parameter determination exercise spends an awful lot of time, people spend an awful lot of time is avoiding spatial aliasing. I wish I had the time to get into temporal and spatial aliasing. Basically, you should sample enough to discern a feature from one another. And determine station spacing and bin size in 3D acquisition to avoid spatial aliasing is an absolute important step. Of course, the next bit is about selecting and designing the source in land. Where do I go for dynamite? Do I go for vibrosize? What type of vibrosize? And then also in marine, it is usually the size and design of the airgun arrays. I mean, do I take short pointed sources or do I take broad sources? Do I need more low frequency or more high frequency? Those kind of questions. Onshore, you have a specific case, again, ground roll rules it. What should be the length of your geophone array? So that half the geophones go up while the other half comes down and you're reducing ground roll at acquisition. Again, anybody who is keen on processing will understand this bit, that the survey area and the migration operator is also a very important test done. That up to what extent, if you think of your survey area as a rectangle, at the edge of that rectangle, I want fully migrated data. So if you think of a three-dimensional spherical aperture, you should have enough coverage outside of that rectangle. So think of a bigger rectangle where you can actually take the data and migrate it to your area of interest. So your migration aperture determination is very important. last but not the least is the 3D geometry. I mean, these two photos are classic example. End-on parallel shooting is usually done in marine surveys, usually in areas where you are near locality or transition zones. You do a lot of non-parallel surveys. Land, at least most of the land surveys I've been associated with, it is aerial geometry where you have the short lines going orthogonal to the receiver spread. This is also done for sea bottom nodes and OBC, but then that's something which Shubhro, I'm sure, will deal with when he talks about PRM on Sunday. So, we, as the geology and geophysics teams, we plan specific surveys to gather detailed information. Again, this is a schematic that I have used for how in land, especially land vibrosis, how does it look like, how the pilot sweep is sent from the vibrator plate. We have a number of things that we need to bear in mind to get the best coupling and then to make sure that the signal to noise ratio is good for the data. You have a recording truck. I mean, in this case, the scheme that I'm showing is an end-on kind of shooting. The other bit is on land. There is a choice of suitable geophone accelerometer. It is very important to reduce signal distortion while increasing bandwidth. So something called the maximum displacement sweep allows seismic vibrators to optimally deliver the required source output. Sometimes we are not in a position to use vibrator given how rugged the earth is. You may not get decent coupling. In that case, we'll have to end up using dynamites. So again, we need to be very cautious about what kind of charge size do we use, what kind of array designs do we use. And then last but not the least, we now use alternate source seismic, especially electromagnetic and passive seismic, which certainly have been used in the recent past. I've just included a split spread short record, which I had at my disposal from Western GECO, just showing how severe sometimes. I mean, this is not too bad actually, but sometimes if you can see if I could get to the cursor, yeah, the ground roll in the data. So these are removed at the processing stage. Now, going to the next schematic, this is all about marine acquisition. And what I've also done is labeled some of the key acquisition parameters in an end-on marine spread, where you've got source depth and receiver depth as two key parameters on the bandwidth of your data. In other words, the source depth and your receiver depth has a big impact on what your ghost notch is going to be, which I'm sure you'll cover in your syllabus. And we can control what that ghost is going to be by choosing what the depth is going to be. Again, how operation parameters determine what kind of spread length that you're going to have, because spread length gives you the freedom to look at data which are fairly deep, and it also gives you low frequency from those depths. What else? The sources, we are mainly using air gun in marine survey, but there's also something called an aqua pulse or a water gun that is used. This is a schematic of, as I said, a streamer which is spread out, and these are air gun arrays. So this boat actually is towing two sources, what we call flip-flop shooting. So one gun fires, and 25 meters down the line, the second gun fires, and then again back to the first gun, and so on. And the streamers record continuously. The two photos that I took, this was back when I used to be on seismic boats, on what the streamer deck and actually the streamers look like. These are all filled. These are electronics, but they're all filled with kerosene in the pipe. And this one is what I'm trying to do, a very simple cartoon of what a stat trace coming out of a processed data from streamer shooting is trying to do to mimic what the subsurface, in this case a fault plane, looks like. Okay, so this is all in 2D. Obviously, the Earth is not 2D. We know it is three-dimensional. Hence, in 3D acquisition, the goal is to sample the full 3D wave field and as many azimuths as possible, and to work towards as basically the Earth is complex, and that complexity needs to be captured and brought to the workstation for an interpreter to deal with it. Acquisition and processing has a huge capability to almost iron out some of these complexities. Could be due to the limitation of acquisition or simple, to crude processing. And what we get at the workstation has very little resemblance to what the Earth actually looks like. I mean, speaking of which, this is a typical what we call a brute stack that is given. This was on board. The processors would have some kind of a regional velocity function. They would stack the gathers, apply some swell noise attenuation, and bingo, you've got a stack. We can't do much with these stacks. It's full of noise. So you need a full-on processing. And again, Partho will cover that tomorrow on how a brute stack becomes a fine-tuned interpretive stack at the end. Okay, let me now move on to 4D seismic. 4D seismic is again a geophysicist's bread and butter. In fields where 4D work, there is a lot of scope to provide a fantastic value that a geophysicist has to offer through analyzing 4D data. Saturation, pressure, and or overburden thickness changes. What do I mean by saturation changes? Gas breaking out in oil, fluid sweep, or the contact, an oil-water contact movement. These are all saturation changes. What do I mean by pressure changes? You will have depletion. As your water comes and replaces the pore spaces and your hydrocarbon is being drained towards the well, you will have depletion. Your pressure will go down. The drawdown will go down. You will also have pressure up, because if you have an EOR scheme in place and you are injecting water into the subsurface, so you'll have depletion as well as pressure up. So pressure changes is a vital parameter that we measure with 4D. And also in some cases, you have, when I say overburden or reservoir thickness changes, what I mean is compaction or relaxation. You actually get stress arches built up. In some of the prospects where I've worked, especially with chalk around, you get a lot of stress arches built up in the overburden due to compaction. Again, 4D is a great tool to measure that. I mean, I included this screenshot simply because I wanted to show between what is called a 3D baseline, the first survey, and the 4D monitor, which is the repeat survey. You see the big change, and this change is the movement of the oil-water contact. This is usually, say, in a year 2014, and this is shot in 2018. And for 4 years, the well here, this dry oil producer, has been in production mode as it is sucking. The oil-water is slowly coming close to the producer, and what we are trying to do is monitor how well that progress is. For example, if this well is faltering, can I drill another well? Is it going to water out very quickly, or should I left? These are the kind of decisions you can take with 4D. Again, I've covered most of this in the conversation. This is a cartoon that I kept to talk about the whole essence of timestamps. Our challenge is to isolate the signal that changes with time between these two surveys and distinguish it from the background noise. It's easier said than done. 4D processing is perhaps one of the most difficult parts of processing, where reducing background noise sometimes becomes a huge challenge, and 4D projects to interpreters don't really add much value. Okay, as I promised, I'm on my last slide, which is focusing on some of the novel areas. No longer novel when you think Broadsize has been around for nearly 10 years, but I thought I'll still mention it. It is one of the broadband acquisition technologies. Broadsize is used by CGG using Slant Streamer. There are others, GeoStreamer from PGS and the Western Geco. When they had a seismic data acquisition service, they used to have something called isometrics. Now, these were all introduced about 10 years ago, and if you look at the data, the left being your conventional versus the right being your broad-size data, one of the first things that comes to your eyes is, wow, where are all my reflectors gone? But then you find out your reflection in your conventional data has a lot of side lobe energy. And broadband data basically takes care of that side lobe energy and removes it. So what you have is your fault planes coming out really nicely. And what you also see, a lot of details shown the noise in your data. So other than broadband data, what I thought I will also include is this appetite for azimuth-rich data, especially in the Gulf of Mexico. Vishal can correct me, but deep azimuth, wide azimuth, multi-azimuth data to undershoot underneath salt dye piers and giant production platforms. You can't take a seismic boat there. How are you going to shoot? So extra survey azimuth adds vital information that facilitates more accurate modeling of complex structures. So these are the two things that I had. I will just mention some of the other areas in acquisition which has been in research for a long time, and they're being tested as we speak. I mean, marine vibrator comes to mind. CGG certainly has done a lot of continuous recording. What do I mean by continuous recording? That even when the vessel is turning, they keep on shooting with longer offsets and recording while turning. That's a great concept which started a few years ago. And of course, you've got OBC and nodes, which are used for permanent reservoir monitoring. Again, something to watch out for next Sunday. So that brings me to the close of my presentation. And I have, I think, overshot my time. I've only left, 5 minutes for Q&A. Apologies for that. Over to you, Ishika.